Welcome to the third video in Special Relativity 2. So in this video we will be looking for an equivalent to Newton's second law, a relativistic equivalent, and in doing so we will start to look at relativistic momentum. So Newton's second law says that F equals ma. And what that implies is that the more force we can apply to a particle or an object, the faster we can get it to move. So that is that there is no limit to the speed that we can get an object to move at. So we in principle can have something moving with a velocity greater than the speed of light. We know that can't be, and so then we can see that this equation F equals ma must break down at relativistic conditions. So what we need are some equivalent fundamental laws of motion that also hold at relativistic speeds. So since F equals ma, and it also equals the rate of change of momentum, the place that we'll start looking is momentum, and the reason is because of the proof of M-inertia. So M-inertia's proof that momentum must be conserved is an incredibly powerful proof, and so if it holds at low speeds, it must also hold at high speeds, at relativistic speeds. So we'll start with that. And in order to do that, we will start by looking at an elastic collision that's happening in relativistic reference frames. So this is our setup. We have, once again, our astronaut in his rocket ship, which is the red rectangle, and it's travelling to the right with a velocity u relative to our space mechanic in his garage. So both the spaceman and the mechanic have a tennis ball. We'll call the one the mechanic has A, and the one that the spaceman or the astronaut has is B. Both tennis balls are exactly the same, and they each throw their tennis balls with exactly the same velocity as they measure it, and they throw them such that the two tennis balls collide and bounce back. And we choose, in this case, that the collision is elastic. So that means that tennis ball B moves with the initial and final velocities vi dash and vf dash. I know this is not the normal notation for initial and final velocity, but in this case we need to distinguish very clearly again between the object, which is the tennis ball, and the reference frame, which is the spaceship. So the object will always have a velocity v, and the reference frame will always have the velocity u, and so we're using now vi and vf for the initial and final velocities. And likewise, the ball A that the mechanic throws will have an initial and final velocity vi and vf. So from the point of view of the astronaut, he throws his ball directly downwards, so directly in the y direction. We'll say down is negative. So directly in the negative y direction. So the velocity of his ball B in the x direction is always 0, before and after the collision, from his point of view. And the velocity of the ball in the y direction initially is negative, so he throws it with an initial velocity of vy0 in the negative direction, and it bounces back from an elastic collision with the same velocity, or the same speed, but in the opposite direction. So its final velocity, as he sees it, as the spaceman sees it, is vy0. And the space mechanic does exactly the same thing. So he throws his ball directly up, and it comes straight back down. So he sees that his ball also has a velocity of 0 meters per second in the x direction, and a speed of vy0 in the y direction. In his case, his initial velocity is upwards, so his initial velocity is positive, and his final velocity is negative. So from each of their individual points of view, those balls behave exactly the same. So now what we're going to do is we will look at this collision from the point of view of the mechanic. So from his point of view, we know how he sees his ball A. He sees that his ball has 0 velocity in the x direction and a speed vy0 in the y direction. When he's looking at ball B, so the ball thrown by the astronaut, that ball is moving with the reference frame of the rocket ship. It's moving inside the rocket ship. So that ball is moving with a velocity u to the right compared to our spaceman. To find the velocity of the ball B in the y direction, as seen by the mechanic, we do need to do our Lorentz transform. And we know that to do a velocity transform in the y direction, for an object moving in the y direction, when its reference frame is moving in the x direction, we get this equation. So Vy is equal to Vy dash divided by gamma times 1 plus u times Vx dash divided by c squared, where Vy dash and Vx dash are how the astronaut sees ball B move. And we saw on the previous slide that the astronaut sees that ball B has a velocity of 0 in the x direction and an initial velocity of negative vy0 in the y direction. So that gives us that our initial velocity of ball B, as seen by the mechanic, is equal to negative vy0 divided by gamma. And we do exactly the same calculation to find the final velocity, and we find that it's equal to vy0 on gamma. So now that we have all of the velocities and all of the masses of all of the components in the system, so of our two balls, as viewed from the same reference frame, we can look at the conservation of momentum. So to simplify things down, I'm going to look only in the y direction at the conservation of momentum, because we know if momentum is conserved, it must be conserved individually in each of the x, y, and z directions. So by our equation for the conservation of momentum, and using our classical equation that momentum is equal to mv, we get this equation here. So that the initial momentum of the system, which is the mass of ball A times its initial velocity plus the mass of ball B times its initial velocity, must equal the final momentum. And I've distinguished between mass A and mass B here, although I have said that they are the same for reasons that will become apparent. So when we substitute in our values for the velocities and simplify down, we get this equation here. So we can see that those two sides are not equal. So using our classical definition of momentum and the assumptions that go with it, we can see that momentum is not conserved. And so returning to Emmy Noether, we know that by her proof, if the laws of physics are the same in all reference frames, then momentum must be conserved. And we already discussed what would happen if the laws of physics are not the same in all reference frames. That would mean that for every time an object is moving with a different velocity, for every different velocity, we would be existing in a different universe. So momentum has to be conserved. And so for momentum to be conserved, since our classical definition didn't work, we need to look at a different definition of momentum. So we'll do the same trick that Lorentz did for his transforms for position and time. And we say that, well, we know the classical term is p equals mv, and we know that works for classical speeds. And so we'll assume that the relativistic momentum has a similar format, that is equal to some function a times mv. And so to find what that function is, we will look again at our conservation of momentum equation. So our p final equals p initial, the simplified format that we found on the last page. And when we simplify that down, we can cancel the 2 on each side, and we also know that uy0 is the same term. So that gives us this equation here, that ma is equal to mb divided by gamma. And when we substitute in our value for gamma, that gives us that ma is equal to mb times the square root of 1 minus u squared on c squared. So to understand what each of those terms mean, we need to remember that we're looking at this from the point of view of the mechanic. And from the point of view of the mechanic, that mass ma is at rest, and the mass mb is moving with some velocity u relative to our mass ma. So from the equation, we can see then that since u squared on c squared is always less than 1, it means that our mass measured when it's moving with a relativistic velocity is greater than the mass measured when it's at rest. So we're going to rewrite that equation just slightly to use more standard terms, and we say that our rest mass, so in our example the mass ma, is equal to the mass moving with a relativistic velocity, so we call that mass m dash because it's in our reference frame s dash, times the square root of 1 minus u squared on c squared. And so that velocity u is the velocity of the reference frame of our mass m dash. So that is the relative velocity of our mass m dash as measured by our observer. And so that gives us a more precise and more formal definition of our relativistic momentum. Instead of saying it's equal to some constant or some function a, mv, we can now define it particularly that our relativistic momentum is equal to gamma times the rest mass of our object times the relative velocity of our object compared to the observer.